Hello and welcome to the Sleepy Astronomer. I'm delighted you found your way here to this peaceful corner of the cosmos where wonder meets rest and where we gently wander through the universe one quiet question at a time. This is the place designed to help you relax, wind down, and maybe even learn a thing or two on your way to sleep. Where in the world are you listening from right now? And what time is it there? I'd love to hear in the comments. It's always a gentle joy to see where across our planet you're drifting off to sleep, or perhaps just taking a moment to pause and breathe, whether you're curled up in bed in Tokyo as the sun rises, or settling into your favourite chair in London as evening falls, or anywhere else on this spinning world of ours. You're exactly where you need to be. If you're new here, welcome to our little community of cosmic wanderers. And if you've been with me before, thank you for returning. It truly means the world to me. If you find tonight's gentle journey through space interesting, or if it helps you unwind even a little bit, I'd be grateful if you'd give this video a like. It's one of the simplest ways to help other people discover these peaceful moments among the stars. And if you'd like to travel with me again, consider subscribing. The notification bell will gently let you know when there's another cosmic journey waiting for you. Speaking of journeys, do you have any topics you'd like me to explore in future videos? Perhaps there's a planet that's caught your curiosity, or a cosmic phenomenon you've always wondered about. Drop your suggestions in the comments below. I read every single one, and your ideas often become the seeds for new adventures through space. Tonight, we're turning our gentle gaze toward our most familiar celestial companion, the Moon. Now, I'll do my best not to make this too fascinating. I'd hate for you to stay awake from sheer lunar excitement. But if you do end up wide-eyed at 3 a.m. contemplating tidal forces and orbital mechanics, at least you'll be able to explain to your cat or dog why the Moon is slowly drifting away from Earth at about the same rate your fingernails grow. You've probably noticed it before. Those nights when sleep seems just a little more elusive, when you find yourself tossing and turning despite feeling tired. You might glance at your clock, wondering what's different about tonight. And sometimes, if you look out your window, you'll see it. A bright, full moon hanging in the darkness, casting silver shadows across your room. Is it coincidence? Or is there something more to this ancient dance between Earth, Moon, and the rhythms of life itself? Tonight, we're going to explore that question together. We'll wander through the Moon's subtle influence on everything from your sleep cycles to the very existence of complex life on Earth. We'll discover how this celestial companion has been quietly shaping our world for over 4 billion years, stabilizing our climate, stirring our oceans, and even protecting us from cosmic threats we rarely think about. We'll journey through humanity's long relationship with lunar light, how civilizations have used the Moon to mark time, navigate vast oceans, and tell stories that still echo in our collective memory. And we'll uncover the remarkable science behind the Moon's formation, its slow drift away from Earth, and the profound ways it continues to influence our planet even now. But perhaps most wonderfully, we'll come to understand how the Moon's presence makes Earth not just habitable, but uniquely suited for the kind of complex, beautiful life we see all around us. From the tidal pools where life first ventured onto land, to the stable seasons that allowed civilizations to flourish, the Moon's influence threads through nearly every aspect of our existence. Before we begin, a gentle reminder that this content is created for educational and relaxation purposes only, and is not intended as medical advice. If you're experiencing persistent sleep difficulties, it's always wise to consult with a healthcare professional. So, get comfortable wherever you are, Take a slow, deep breath and let your shoulders relax. If you can see the moon from where you're resting, take a moment to appreciate that ancient light. And if you can't see it tonight, don't worry. It's still there, still pulling gently at our oceans, still keeping watch over our spinning world. Let's begin this peaceful journey together, drifting softly into the gentle mysteries of moonlight and discovering just how deeply connected we are to that bright companion that has been lighting Earth's nights since long before the first human looked up at the stars in wonder. Let's start with something you might recognize. Picture this. It's been a long day, you're genuinely tired, and you settle into bed expecting to drift off quickly. But instead, you find yourself lying there, mind oddly alert, thoughts spinning in gentle circles. You check the time, 11 p.m., midnight, 1 a.m., and still sleep feels just out of reach. Finally, perhaps frustrated, you glance toward your window, and there it is, a brilliant full moon, flooding your room with silver light. Coincidence? Many would say so. But humans have been noticing this connection for thousands of years, long before we had electric lights to mask the moon's presence, long before we understood the intricate biology of sleep itself. The ancient Greeks had a word for this. They called people who seemed affected by the full moon moonstruck, or lunatic from Lunar, their name for the moon. The Romans noticed it too, as did cultures across the world. Chinese medicine speaks of lunar cycles affecting the body's energy, describing how the moon's phases influence the flow of qi through our bodies. Indigenous peoples from the Arctic to the Amazon developed entire calendars around not just the moon's phases, but the subtle changes in human behavior and health they observed during each phase. The Inuit people of the Arctic have dozens of words for different types of moonlight, recognizing subtle variations in how lunar illumination affects both human behavior and animal activity. In the Amazon, indigenous shamans have long used lunar calendars to determine the best times for healing ceremonies, believing that the moon's phases influence the potency of medicinal plants and the receptivity of the human spirit to healing. In ancient Egypt, physicians prescribed different treatments based on lunar phases, believing that the body's ability to heal varied with the moon cycle. Medieval European monasteries scheduled their prayers and contemplative practices around lunar rhythms, finding that certain phases enhanced spiritual receptivity and inner peace. Were they simply imagining patterns that weren't there? For most of modern history, scientists thought so. The moon, after all, is 250,000 miles away. Surely something so distant couldn't influence something as complex and individual as your personal sleep cycle. But here's where the story becomes fascinating. In recent decades, researchers have begun uncovering evidence that those ancient observations might not have been mere superstition after all. In 2013, scientists at the University of Basel in Switzerland conducted a study that would make those ancient stargazers smile knowingly. They looked at sleep data from 33 people over several years, carefully tracking how participants slept during different lunar phases. What they found was remarkable. Around the full moon, people took an average of 5 minutes longer to fall asleep. They slept about 20 minutes less overall. And perhaps most intriguingly, their levels of deep sleep, that crucial restorative phase where your body repairs itself and your mind processes the day's experiences, decreased by about 30%. Now, this wasn't because of moonlight streaming through windows. The study participants were sleeping in completely dark rooms, with blackout curtains and no clocks or calendars visible. They had no way of knowing what phase the moon was in. Something else was at work. The researchers also measured melatonin levels, the crucial hormone that helps regulate your sleep-wake cycle. They found that during full moon periods, participants' bodies produced lower levels of melatonin, as if some invisible signal was telling their brains to stay more alert. This discovery sent ripples through the sleep research community because it suggested that the moon's influence might be operating at a fundamental biological level. Other studies have found similar patterns. Research from Sweden showed that people's sleep efficiency, how much of their time in bed they actually spend sleeping, varies with lunar cycles, with the lowest efficiency occurring around the full moon. Studies from Italy found that children whose sleep patterns are often more sensitive to external influences showed even stronger correlations with lunar phases. Children took longer to fall asleep and experienced more restless sleep during full moon periods. A fascinating study from the University of Washington examined 3 different communities: urban residents in Seattle with full access to electric lighting, rural residents of Washington state with some artificial lighting, and indigenous communities in Argentina with minimal artificial lighting. Remarkably, all 3 groups showed lunar sleep patterns, but the effect was strongest among those with the least artificial lighting, suggesting that while electric lights might mask the moon's influence, they don't eliminate it entirely. But how could this possibly work? How could an object 250,000 miles away influence the firing of neurons in your brain, the release of hormones in your bloodstream, the gentle ebb and flow of your circadian rhythms? The answer lies in something extraordinary about life on Earth. We are, quite literally, children of the tides. Think about it this way. Your body is roughly 60% water. That water exists in your blood, coursing through vessels so narrow that individual red blood cells must line up single file to pass through them. It exists in the fluid between your cells, creating the medium through which nutrients and waste products travel. It exists in the delicate spaces of your brain, where the slightest changes in pressure or chemistry can affect consciousness itself. And just as the moon's gravitational pull draws our oceans into tides, those massive, twice-daily movements of water that have shaped coastlines for billions of years, it also exerts a subtle pull on the water within you. Now, the moon's effect on your body's water isn't anywhere near as dramatic as ocean tides. The gravitational force is incredibly small on such a tiny scale. If you were to weigh yourself on an extremely sensitive scale during different lunar phases, you might detect a difference of a few thousandths of an ounce, barely measurable even with the most precise instruments. But remember, your brain, your nervous system, your entire consciousness emerges from incredibly delicate electrical and chemical processes that might be sensitive to influences we're only beginning to understand. Consider the human brain for a moment. It contains roughly 86 billion neurons, each connected to thousands of others through synapses that communicate using electrical impulses and chemical messengers. The total number of connections in your brain exceeds the number of stars in the observable universe, and all of this extraordinary complexity operates on incredibly small amounts of energy. Your entire brain uses about as much power as a dim light bulb. With such delicate, finely tuned processes, it's not inconceivable that even tiny gravitational influences could have measurable effects. Some researchers have proposed that the moon's gravitational pull might slightly alter the pressure of cerebrospinal fluid, the liquid that cushions your brain and spinal cord. Others suggest that lunar gravity might influence the behavior of ion channels in neurons, those microscopic gates that control the flow of electrically charged particles across cell membranes. There's another possibility, one that reaches even deeper into the story of life itself. For nearly 4 billion years, Earth's creatures have evolved under the steady rhythm of lunar cycles. The moon has been our planet's companion for so long that it's possible, just possible, that some fundamental aspects of how life operates have become synchronized with its presence. Consider the fiddler crab, scuttling along beaches worldwide. Even when researchers bring these creatures into laboratories with no windows, no natural light, no way of sensing the outside world, they continue to follow lunar rhythms with uncanny precision. Their activity peaks and valleys align with the tides they can no longer sense, as if the moon's cycle has become written into their very cells. The rhythms are so precise that researchers can predict a fiddler crab's behavior simply by consulting a lunar calendar. When the moon is pulling most strongly on the Earth's oceans, creating the highest tides, laboratory crabs become most active, scurrying about their artificial environments as if preparing for the tidal abundance their ancestors relied upon for food and reproduction. Or think about the grunion, those slender fish that dance onto California beaches to spawn. They time their reproduction not just to the phases of the moon, but to specific combinations of lunar and solar tides, emerging from the ocean during the highest tides of the year, with clockwork precision that has amazed observers for centuries. Female grunion ride the waves onto sandy beaches, dig themselves tail first into the sand, and deposit their eggs just below the surface. Males wrap around the females, fertilizing the eggs in a silvery dance that lasts only seconds before both fish return to the sea. What's remarkable is that the eggs develop in the sand for exactly 2 weeks, the time it takes for the moon to cycle from one set of extreme tides to the next. The baby grunion hatch just as the next set of high tides arrives to wash them out to sea. It's as if these fish have internalized the moon's rhythm so completely that their entire reproductive cycle is synchronized to lunar time. Coral reefs across the world's oceans release their eggs and sperm in massive synchronized events timed to lunar cycles, creating underwater snowstorms of life that depend on this celestial timing for their survival. On the Great Barrier Reef, this spawning occurs on just a few nights each year, always in the week following the full moon in November or December. Scientists believe the corals use a combination of water temperature, daylight hours, and lunar cycles to coordinate this spectacular event. When coral spawning occurs, the water becomes thick with billions of eggs and sperm, creating a fertility soup that feeds countless other marine creatures. The timing is crucial. Spawn too early or too late, and the eggs and sperm won't find each other in the vast ocean. The moon provides the precise timing signal that ensures reproductive success. Even plants seem to sense the moon's presence. Some species of algae show lunar rhythms in their growth and reproduction, their cellular processes speeding up and slowing down in patterns that match the moon's phases. Certain trees have been observed to show subtle changes in their sap flow that correlate with lunar phases, not enough to affect the tree's health, but measurable with sensitive instruments. Traditional farmers have long planted and harvested according to lunar calendars, believing that the moon's phases affect plant growth. While scientific evidence for direct lunar effects on agriculture is mixed, some studies have found correlations between lunar phases and seed germination rates, suggesting that even plant biology might retain traces of ancient lunar rhythms. If the moon's influence can reach into tide pools and coral reefs, into the cellular processes of creatures great and small, is it really so surprising that it might touch the delicate symphony of human sleep as well? Your circadian rhythm, that internal clock that tells your body when to feel alert and when to feel sleepy, is one of the most fundamental aspects of being alive. It's controlled by a small cluster of neurons in your brain called the suprachiasmatic nucleus, a tiny biological timekeeper that responds to light, temperature, and other environmental cues to keep your body synchronized with the turning of the Earth. This internal clock is remarkably precise, keeping time to within minutes even when you're isolated from all external time cues. But it's not a rigid, unchanging mechanism. It constantly adjusts itself based on environmental signals, helping you adapt to seasonal changes in daylight, to jet lag when you travel across time zones, to shift work schedules that disrupt normal sleep patterns. Perhaps it responds to other rhythms too. Perhaps woven into the very fabric of how your brain regulates sleep and wakefulness, there are echoes of older rhythms, deeper cycles that connect you not just to the spin of the Earth, but to the slow dance of Earth and Moon together. Some researchers have found that people's circadian rhythms show subtle variations that align with lunar cycles. Not dramatic changes, but small shifts in the timing of body temperature fluctuations, hormone release, and other biological processes that help regulate sleep and wake cycles. There's also evidence that the moon might influence the production of certain neurotransmitters, the chemical messengers that neurons use to communicate with each other. Serotonin, which plays a role in mood regulation and sleep, shows cyclical variations that some studies have linked to lunar phases. GABA, a neurotransmitter that promotes relaxation and sleep, might also be influenced by lunar cycles, though the research is still in its early stages. This doesn't mean the moon controls your sleep, or that you're helpless in the face of lunar phases. Your sleep is influenced by countless factors. What you ate for dinner, how much sunlight you saw that day, whether you spent the evening looking at screens, how much stress you're carrying from work or relationships, the temperature and humidity of your bedroom, the comfort of your mattress and pillows, the sounds and smells in your environment. The moon's influence, if it exists at all, is subtle, gentle, one quiet voice in a complex choir of biological rhythms. Most nights, you probably don't notice it at all. But occasionally, on those nights when sleep feels mysteriously elusive despite your tiredness, when you find yourself lying awake with a mind that refuses to quiet, it might be worth glancing out your window to see if a bright moon is keeping watch over your restless thoughts. But there's something beautiful about the possibility, isn't there? The idea that even as you lie in your bed, in your human-made shelter, surrounded by the artifacts of modern civilization, you might still be connected to something vast and ancient. That the same force that stirs the oceans and guides migrating animals might also whisper to the deepest parts of your nervous system, reminding you that you are not separate from the natural world, but part of it. Ancient peoples understood this connection intuitively. They planned their lives around lunar calendars, not just for practical reasons, though the moon's light certainly helped them navigate dark nights and time their activities, but because they sensed something deeper. They knew that humans, like all of Earth's creatures, are not independent entities floating in a void, but participants in a cosmic dance that has been unfolding for billions of years. In many traditional cultures, sleep itself was seen as a time when the boundaries between the individual and the cosmos became more permeable. Dreams were viewed as journeys into other realms, and the moon was often seen as a guide or guardian of these nocturnal travels. The Lakota people spoke of the moon as a grandmother who watches over sleeping children, protecting their dreams and ensuring their safe return to the waking world. Celtic traditions associated different moon phases with different types of dreams: the new moon for dreams of new beginnings, the waxing moon for dreams of growth and possibility, the full moon for dreams of revelation and insight, the waning moon for dreams of release and letting go. Modern sleep research has begun to uncover some fascinating connections between lunar phases and dream content. Some studies suggest that people report more vivid, memorable dreams during full moon periods, the same times when their sleep tends to be lighter and more easily disrupted. It's as if the moon's influence makes our sleep more active, more dynamic, blurring the boundaries between conscious and unconscious experience. Other research has found that people's sleep patterns show individual variations in lunar sensitivity. Some people seem completely unaffected by moon phases, sleeping soundly regardless of what's happening in the sky above. Others show strong correlations between lunar cycles and sleep quality, as if their internal clocks are more closely attuned to celestial rhythms. Interestingly, lunar sensitivity seems to be more common in people who spend more time outdoors, who are more aware of natural cycles, or who live in areas with less light pollution. It's as if constant exposure to artificial light and urban environments can partially mask our connection to lunar rhythms, but doesn't eliminate it entirely. Tonight, as you feel yourself drifting towards sleep, whether easily or with the gentle restlessness that sometimes comes with full moons, you might take a moment to appreciate this mystery. The moon that hangs in your sky tonight is the same moon that has witnessed the entire story of life on Earth. It has watched over the first creatures to crawl from tidal pools onto dry land. It has illuminated the dreams of every human who has ever lived. And now, in ways we're only beginning to understand, it continues its gentle influence, pulling not just to tour oceans, but perhaps at the very rhythms of consciousness itself, connecting you to a story much larger and older and more beautiful than any of us can fully comprehend. Whether the moon's influence on your sleep is real or imagined, biological or psychological, doesn't diminish its significance. The fact that humans across cultures and throughout history have noticed this connection speaks to something deep in our nature, our need to feel connected to the larger rhythms of the natural world, our intuitive understanding that we are part of something greater than ourselves. But what exactly is this mysterious companion that seems to reach so deeply into the fabric of life on Earth? To understand that, we need to journey beyond the gentle effects of moonlight, beyond the whispered influence on tides and sleep, and discover the moon itself. So what exactly is this celestial companion that seems to whisper to the very rhythms of life on Earth? To truly understand the moon's influence, we need to journey back in time, not just to ancient civilizations gazing up in wonder, but to the violent birth of the moon itself over 4.5 billion years ago. Picture the early Earth if you can. It's nothing like the blue marble we know today. This is a hellish world of molten rock and toxic atmosphere, constantly bombarded by asteroids and comets left over from the formation of the solar system. The surface temperature hovers around 2,000 degrees Fahrenheit, hot enough to melt copper. The atmosphere is a poisonous mixture of methane, ammonia, and carbon dioxide, with no oxygen to speak of. The day lasts only about 6 hours because Earth is spinning much faster than it does now, completing a full rotation in the time it now takes for you to sleep through a single night. There are no oceans yet, no continents as we know them, certainly no life. The early Earth is a world in chaos, still cooling from its formation, still being shaped by the violent processes that created our solar system. Lightning constantly flickers through the toxic atmosphere, and volcanic activity is so intense that entire regions of the surface are covered in rivers of molten lava. Into this chaos comes an object roughly the size of Mars. Scientists have named it Theia, after the Greek Titaness, who gave birth to the moon goddess Selene. Theia is itself a planetary embryo, one of many such objects that formed in the early solar system, but failed to become a full-fledged planet. For millions of years, Theia has been wandering the inner solar system in an increasingly unstable orbit, gradually drawn toward the young Earth by gravitational interactions with the other forming planets. The collision, when it finally comes, is inevitable. These two worlds have been locked in a gravitational dance that can only end one way, with a catastrophic impact that will reshape both objects forever. Try to imagine the scale of this impact. We're talking about two planetary bodies, each thousands of miles across, colliding at speeds of several miles per second. The energy released is beyond anything in human experience, millions of times greater than all the nuclear weapons ever built, going off simultaneously. It's an event so violent that it briefly creates temperature comparable to the surface of the sun. The collision doesn't just dent or crater the Earth, it partially vaporizes both worlds. The impact occurs at a glancing angle, which proves to be crucial. A head-on collision would have shattered both objects completely, leaving nothing but a field of debris that would eventually fall back to the sun. Instead, the angled impact tears away a significant portion of both Earth and Theia, hurling massive chunks of molten rock into space. Some of this debris escapes Earth's gravity forever, lost to the depths of space. Some falls back to Earth, adding to the hellish conditions on our planet's surface and contributing to a period scientists call the Late Heavy Bombardment. But a significant amount of the debris, a mixture of material from both Earth and Theia, begins to orbit our wounded world in a ring of molten rock and vapor. And here's where something almost magical happens. Over the course of just a few thousand years, an eye blink in geological time, this ring of debris begins to clump together under its own gravity. Larger pieces attract smaller ones through gravitational attraction. Gradually, inexorably, the scattered remnants of two worlds coalesce into a single new body, our moon. This process, called accretion, is both violent and beautiful. As chunks of rock collide and stick together, the energy of these impacts generates enormous heat, keeping the forming moon molten for hundreds of thousands of years. The moon begins as a ball of magma, glowing red-hot in Earth's sky like a second, smaller sun. This story might sound like science fiction, but it's our best explanation for a series of lunar mysteries that puzzled scientists for centuries. Why does the moon have such a relatively small iron core compared to its overall size? In the giant impact scenario, most of the iron from both Earth and Theia would have settled into Earth's core, while the moon formed primarily from the rocky mantles of both worlds. Why is the moon's composition so similar to Earth's mantle? Because a significant portion of the moon literally is Earth's mantle, blasted into space and reformed. When scientists compare the isotopic composition of lunar rocks brought back by the Apollo missions with rocks from Earth's mantle, they find striking similarities that can only be explained if both formed from the same source material. Why does the Earth-Moon system have such unusual angular momentum, the measure of rotational motion, compared to other planets? The giant impact theory explains this too. The collision didn't just create the moon, it also gave the Earth-Moon system a spin that accounts for our current day length and the moon's orbital motion. The giant impact theory, as it's known, answers all these questions elegantly. The moon is literally part of the early Earth, blasted into space and reformed in orbit around us. In a very real sense, when you look up at the moon, you're seeing a piece of our own world, transformed and made distant, but forever connected to us by gravity and shared origin. But that's just the beginning of the moon's remarkable story. In those early days, the newly formed moon was much, much closer to Earth than it is today, perhaps only about 15,000 miles away compared to the current distance of roughly 240,000 miles. Imagine looking up and seeing the moon filling a significant portion of your sky, appearing perhaps 15 times larger than it does now, so large that it would stretch from horizon to horizon when directly overhead, a dome of silver light covering much of the visible sky. At that distance, the moon's gravitational effects would have been extraordinary. Tides wouldn't have been measured in feet, but in hundreds of feet. Imagine ocean tides 1,000 feet high, massive walls of water that would have reshaped coastlines with every cycle. The solid Earth itself would have been stretched and compressed by tidal forces so strong that the planet's surface would have risen and fallen by hundreds of feet, twice each day. The moon would have raced across the sky, completing an orbit in just a few hours rather than the 28 days we're accustomed to now. Earth's rotation would have been so fast that sunrise and sunset would have occurred every few hours, creating a world of rapid, constant change where day and night alternated with breathtaking speed. And here's something beautiful. From the very beginning, the moon and Earth have been engaged in a kind of cosmic dance, each changing the other through their gravitational embrace. The massive tides raised by the close moon gradually slowed Earth's rotation through friction, stretching our 6-hour day to the 24-hour cycle we know today. Meanwhile, Earth's gravity gradually pushed the moon away, causing it to spiral slowly outward to its current distance. This process is still happening, though at a much gentler pace now that the moon is farther away. Every year the moon moves about 1.5 inches farther from Earth, roughly the same rate at which your fingernails grow. It's imperceptible in human timescales, but over millions and billions of years, it adds up to profound changes. Scientists can measure this drift with incredible precision using laser reflectors left on the lunar surface by the Apollo astronauts. By bouncing laser beams off these mirrors and measuring how long the light takes to return to Earth, researchers can determine the moon's distance to within a few centimeters. Over the decades since these measurements began, they've confirmed that the moon is indeed slowly spiraling away from us, just as the theory predicts. But let's bring our focus back to the moon as it exists today, that familiar companion we see hanging in our night sky. What we're looking at is a world both alien and strangely familiar. The moon is smaller than you might intuitively expect, about 1/4 the diameter of Earth, with roughly the same surface area as the continents of North and South America combined. If Earth were a basketball, the moon would be a tennis ball sitting about 24 feet away. Yet despite this relatively small size, the moon appears roughly the same size as the sun in our sky, a coincidence so perfect it allows for the spectacular phenomenon of total solar eclipses. This size similarity is purely coincidental, what astronomers call a cosmic accident. The sun is about 400 times wider than the moon, but it's also about 400 times farther away. This remarkable coincidence means that during a solar eclipse, the moon covers the sun's bright disk almost exactly, revealing the sun's delicate, ethereal corona in one of nature's most breathtaking displays. This cosmic accident has had profound effects on human history and understanding. Total solar eclipses have shaped religions, ended wars, and inspired some of our deepest thoughts about our place in the universe. Ancient Chinese astronomers developed sophisticated methods for predicting eclipses, believing that a celestial dragon was devouring the sun. Greek philosophers used eclipses to calculate the size of the Earth and Moon. Modern scientists have used solar eclipses to test Einstein's theory of relativity and to study the sun's outer atmosphere. Interestingly, this perfect size match is temporary in cosmic terms. As the moon continues to drift away from Earth, it will gradually appear smaller in our sky. In about 600 million years, the moon will be too far away to completely cover the sun, and total solar eclipses will become impossible from Earth's surface. We are living in a brief window of cosmic time when perfect solar eclipses are possible, a window that has lasted for hundreds of millions of years and will continue for hundreds of millions more. The moon's surface tells the story of the solar system's violent youth. Unlike Earth, the moon has no significant atmosphere to speak of. The atmospheric pressure on the lunar surface is less than 1/trillionth of Earth's atmospheric pressure, so thin that it's essentially a vacuum. There's no weather to erode impact craters, no wind to redistribute dust, no precipitation to reshape the landscape. The Moon also lacks the geological processes that constantly resurface our planet. No plate tectonics, no significant volcanic activity, no mountain-building processes. So when you look at the Moon, you're seeing a museum of ancient impacts, craters that formed billions of years ago and remain almost perfectly preserved. Every crater tells a story of cosmic violence, of asteroids and comets that crashed into the lunar surface with tremendous force, excavating vast amounts of rock and creating the battered landscape we see today. Those dark patches you can see with the naked eye, the features that create the man in the moon that many cultures recognize, or the rabbit that others see, are called Maria, Latin for seas. Early astronomers, looking at these smooth, dark areas through primitive telescopes, thought they might actually be bodies of water, hence the name that has stuck to this day. But we now know they're vast plains of solidified lava, formed when massive impacts cracked the moon's crust and allowed molten rock to flow out from the interior and harden on the surface. These Maria are remnants of the moon's early history, when it was still hot enough inside to generate volcanic activity. The largest of these, Mare Imbrium, or the Sea of Rains, is larger than the state of Texas and was formed by an impact so massive that it sent shockwaves around the entire moon. The lighter areas, which make up most of the moon's visible surface, are the highlands, the moon's original crust, blasted and reblasted by eons of impacts, but never covered by the dark lava flows. These highlands are among the oldest surfaces in the solar system, dating back over 4 billion years to the moon's formation. They're made primarily of a rock called anorthosite, composed largely of the mineral feldspar, which gives them their light colour. The difference in crater density between the Maria and the highlands tells us about the timing of major impact events in the solar system's history. The highlands are heavily cratered, covered with overlapping impact scars that speak of intense bombardment. The Maria, being younger, have far fewer craters, showing that the rate of impacts decreased significantly after the Maria formed. And here's something remarkable. We always see the same face of the moon. The moon rotates on its axis at exactly the same rate it orbits Earth, a phenomenon called tidal locking, or synchronous rotation. This isn't a coincidence. It's the result of Earth's gravity gradually slowing the moon's rotation over billions of years until the two became synchronized. Tidal locking occurs because Earth's gravity is stronger on the side of the moon facing us than on the far side. Over millions of years, this gravitational difference created a slight bulge in the moon's shape, with the long axis of this bulge pointing toward Earth. As the moon rotated faster than it orbited in its early history, Earth's gravity pulled on this bulge, gradually slowing the moon's rotation until it matched its orbital period. This means there's an entire hemisphere of the moon that no human saw until the space age. The far side of the moon, often mistakenly called the dark side, though it receives just as much sunlight as the near side, remained a complete mystery until Soviet spacecraft first photographed it in 1959. What they found was surprising. The far side looks dramatically different from the familiar near side. It's even more heavily cratered, with almost none of the smooth Maria we can see from Earth. The entire far side is basically highland terrain, covered with ancient craters, piled on top of ancient craters in a landscape that speaks of incredible violence. Scientists now think this difference exists because Earth's gravity affects the moon's internal structure. The moon's center of mass is actually offset slightly toward Earth, making the crust thicker on the far side and thinner on the near side. When ancient impacts cracked the moon's crust, molten rock could more easily reach the surface on the near side, creating the Maria we see. On the far side, the thicker crust prevented most lava flows from reaching the surface. The moon's interior is as fascinating as its surface. Beneath that ancient, battered crust lies a rocky mantle similar in composition to Earth's mantle, and at the centre a small iron core, much smaller relative to the moon's size than Earth's core is relative to our planet. This small core is probably partially molten even today, generating weak magnetic fields that lunar orbiters have detected. We know about the moon's internal structure thanks to seismic monitoring equipment left by the Apollo astronauts. These seismometers detected moonquakes, some caused by tidal stresses as Earth's gravity flexes the moon, others triggered by meteorite impacts, and some originating deep within the moon's interior. By analysing how seismic waves travel through the moon, scientists have been able to map its internal structure just as they do for Earth. The seismic data revealed some surprises. Moonquakes can last for hours, much longer than earthquakes because the moon's dry, cold interior doesn't dampen seismic waves as effectively as Earth's water-rich interior does. The moon also rings like a bell when struck by large meteorites, with vibrations continuing for hours after impact. But perhaps most remarkably, the moon has no significant magnetic field today, unlike Earth with its protective magnetic shield generated by our planet's molten iron core. This means the moon's surface is constantly bombarded by cosmic radiation and charged particles from the sun, the solar wind. Any atmosphere or surface water that might have existed in the moon's early history would have been stripped away long ago by this constant bombardment. The lack of a magnetic field also means that the solar wind interacts directly with the lunar surface, creating some interesting effects. When solar wind particles strike lunar rocks, they can create a thin, temporary atmosphere of sodium, potassium, and other elements. This atmosphere is so thin that individual atoms rarely collide with each other, but it's detectable by sensitive instruments. Yet amazingly, despite the harsh conditions, we've discovered that water does exist on the moon, not as liquid water, which couldn't survive on the airless lunar surface, but as ice hidden in permanent shadows near the lunar poles, where temperatures are so cold that water ice can survive for billions of years. These permanently shadowed regions exist because the moon's axis of rotation is tilted only about 1.5 degrees relative to its orbit around the sun. This means that the floors of deep craters near the lunar poles never receive direct sunlight, creating cold traps where temperatures remain below -400 degrees Fahrenheit, colder than the surface of Pluto. Multiple spacecraft missions have confirmed the presence of water ice in these lunar cold traps. The water probably came from ancient comet impacts, with the ice sublimating, turning directly from solid to gas, everywhere on the moon except in these permanently shadowed refuges. These deposits represent a treasure trove for future lunar exploration, providing not just water for drinking and growing food, but also hydrogen and oxygen that could be split apart to create rocket fuel. The discovery of lunar water has revolutionized our thinking about the moon's potential as a base for future space exploration. Instead of hauling all supplies from Earth at enormous cost, future lunar colonies could potentially extract water from these polar ice deposits, making long-term lunar habitation much more feasible. The moon's lack of atmosphere creates an environment utterly alien to anything on Earth. There's no air to breathe, of course, but more subtly, there's no atmosphere to moderate temperatures or distribute heat. In direct sunlight, the lunar surface reaches temperatures of over 250 degrees Fahrenheit, hot enough to boil water if any existed on the surface. In shadow, particularly in those permanently shadowed polar regions, temperatures plummet to minus 400 degrees Fahrenheit, approaching absolute zero. This extreme temperature variation happens because there's no atmosphere to trap and redistribute heat. On Earth, our atmosphere acts like a blanket, absorbing heat from the sunny side and carrying it to the shadowed side through winds and weather patterns. The Moon has no such moderating influence, creating a world of temperature extremes. There's no sound on the Moon either. With no air to carry sound waves, the Moon is a world of perfect eternal silence. The only sounds an astronaut would hear would be those transmitted through their spacesuit, their own breathing, their heartbeat, radio communications from Earth or other astronauts. Otherwise, even a massive meteorite impact would occur in complete silence, creating a spectacular explosion of dust and debris that no one would hear. This silence has a profound psychological effect on visitors to the Moon. Apollo astronauts describe the eerie quiet as both peaceful and unsettling. Without the constant background noise we're accustomed to on Earth, wind through trees, distant traffic, birds singing, the hum of appliances, the lunar environment feels almost otherworldly in its stillness. The Moon's low gravity, about 1/6 of Earth's, would make movement feel dreamlike and strange. Everything you're familiar with about how objects move and fall would work differently there. You could jump 6 times higher than on Earth, but you'd fall back down in slow motion, giving you time to appreciate the graceful arc of your movement through the airless environment. Walking would give way to a bouncing gait, as the Apollo astronauts discovered. The combination of heavy spacesuits and low gravity made normal walking inefficient, so the astronauts developed a characteristic bunny hop style of movement that allowed them to cover ground quickly while maintaining balance. Their movements took on an almost ballet-like quality, flowing and graceful in a way impossible under Earth's stronger gravitational pull. Standing on the lunar surface, looking up at the sky, you would see something no human on Earth has ever seen, a black sky filled with stars, even in the middle of the lunar day. With no atmosphere to scatter sunlight, the stars remained visible at all times. The sky would be an infinite dome of perfect black, studded with thousands of stars visible to the naked eye, far more than you can see from Earth even on the darkest night. And hanging in that black sky would be Earth itself. A blue and white marble 4 times larger than the Moon appears from Earth, turning slowly to show the continents and oceans, the swirling clouds and polar ice caps of your home world. Earthrise, as seen from the lunar surface, is one of the most emotionally powerful sights in the solar system, a reminder of home that appears both achingly beautiful and heartbreakingly fragile. The Apollo astronauts described Earth as looking like a precious jewel against the cosmic darkness, a single oasis of colour and life in the vast emptiness of space. This perspective fundamentally changed how humanity thinks about our planet, contributing to the environmental movement and the understanding of Earth as a single, interconnected system. The lunar landscape itself tells stories that stretch back billions of years. Every rock, every grain of dust, every crater wall contains information about the early history of the solar system. Lunar samples brought back by the Apollo missions and robotic probes have revealed that the Moon preserves a record of the solar system's violent youth that has been largely erased from Earth's surface by geological activity. Some lunar rocks are among the oldest materials ever found in the solar system, dating back 4.4 billion years to within a few 100 million years of the Moon's formation. These ancient samples contain tiny mineral grains that formed in the earliest epochs of solar system history, providing scientists with direct physical evidence of conditions during the solar system's birth. The lunar soil, called regolith, is unlike anything on Earth. Created by billions of years of meteorite impacts grinding rock into powder, It's incredibly fine and clingy, sticking to everything it touches. The regolith contains microscopic glass beads, formed when impacts melted lunar rock and sprayed it across the surface, where it cooled rapidly in the vacuum of space. This regolith also contains a record of the Sun's history embedded in its grains. Solar wind particles have been striking and embedding themselves in lunar soil for billions of years, creating a geological record of how the Sun's output has changed over time. Scientists can study ancient solar wind preserved in lunar samples to understand how our star has evolved. The Moon's craters range in size from microscopic pits created by tiny meteorites to enormous basins hundreds of miles across. The largest impact feature on the Moon is the South Pole Aitken Basin, a massive crater on the far side that stretches for over 1,500 miles and is up to 8 miles deep. This impact was so enormous that it excavated material from deep within the Moon's interior, providing scientists with samples of lunar mantle rock that would otherwise be inaccessible. Each crater tells a story not just of the impact that created it, but of the subsequent history of bombardment that has modified it. Smaller craters pepper the floors of larger ones, creating a palimpsest of impacts that scientists can read like a history book. By studying the density and size distribution of craters, researchers can determine the relative ages of different lunar surfaces and understand how the rate of impacts has changed over solar system history. The Moon's geological history can be divided into several major periods. The first billion years, called the pre-Nectarian period, saw the formation of the Moon's original crust and the largest impact basins. This was followed by the Nectarian period, when many of the large impact basins we see today were formed. The Imbrian period saw the formation of Mare Imbrium and other large maria, as well as the last major impact events. Finally, the Eratosthenian and Copernican periods represent the more recent history of smaller impacts and gradual change. This is the Moon that influences our tides and possibly our sleep, the Moon that has been humanity's companion and timekeeper, and inspiration for thousands of generations. It's a world shaped by violence, sculpted by time, locked in an eternal dance with Earth that began in fire, and has continued for nearly the entire history of our solar system. But the Moon's influence on Earth goes far beyond gentle effects on sleep cycles or the twice-daily rhythm of the tides. As we're about to discover, our lunar companion has played a role in shaping not just the surface of our planet, but the very possibility of complex life itself. Now that we understand what the Moon is, this ancient companion born from cosmic violence, locked in eternal synchrony with Earth, let's explore something even more remarkable: how the Moon's presence has shaped not just our planet's surface, but the very conditions that make complex life possible. The story begins with something you've probably witnessed if you've ever spent time near the ocean: the rhythm of the tides. Twice each day, in an endless cycle that has repeated for billions of years, the seas rise and fall in response to the Moon's gravitational pull. But to truly understand how profound this influence is, we need to think about gravity in a slightly different way than we usually do. Most of us learned in school that gravity is the force that keeps us anchored to Earth's surface, the invisible tether that prevents us from floating away into space. And that's true, but gravity has another characteristic that's less intuitive and far more important for understanding the Moon's influence. It gets weaker with distance. The farther you are from a massive object, the less gravitational force you feel. This might seem obvious when you think about it. Astronauts in orbit experience weightlessness because they're farther from Earth's center than we are on the surface. But the implications of this distance-dependent force are more subtle and far-reaching than most people realize. Now, Earth is quite large, about 8,000 miles in diameter. This means that the side of Earth facing the Moon is roughly 8,000 miles closer to the Moon than the side facing away. That might not sound like much compared to the Moon's average distance of 240,000 miles, but it's enough to create a meaningful difference in gravitational pull. Think of it this way. Imagine you're standing on the side of Earth closest to the Moon. The Moon's gravity is pulling on you with a certain force. Now imagine someone standing on the exact opposite side of Earth. They're 8,000 miles farther from the Moon than you are, so they feel slightly less lunar gravitational pull. This difference in gravitational force across Earth's diameter is what physicists call a tidal force. The water on the side of Earth closest to the Moon feels the Moon's gravity more strongly than the water on the far side. This difference in gravitational force causes the water to flow toward the areas where the gravitational pull is strongest, creating the bulge of water we experience as high tide. But here's where it gets interesting, and where many people's intuition fails them. There are actually two bulges of water, one facing the Moon and one on the opposite side of Earth. The near side bulge makes intuitive sense. The Moon is pulling the water toward it. But why should there be a corresponding bulge on the far side? The answer lies in understanding that the Moon isn't just pulling on Earth's water, it's pulling on the entire Earth. The solid Earth itself gets pulled toward the Moon more strongly than the water on the far side. In effect, the Earth is pulled out from under the water on the far side, leaving that distant water behind in a second bulge. It's as if you were holding a ball of soft clay with drops of water on opposite sides. If someone pulled the clay ball toward them, the water drop on the near side would move with the clay, while the water drop on the far side would be left behind as the clay moved away from it. The result would be two water drops, one pulled forward with the clay, one left behind. As Earth rotates beneath these two bulges, any given location experiences two high tides and two low tides each day. This is why, if you live near the ocean, you'll notice that high tide occurs roughly every 12 hours and 25 minutes. The extra 25 minutes accounts for the fact that the Moon is also moving in its orbit around Earth, so it takes a little longer for any point on Earth to line up with the Moon again. This might seem like a simple, even obvious process, but the effects reach far deeper than you might imagine. Those tides don't just move water, they flex and stretch the entire Earth. The solid rock beneath your feet rises and falls by several inches twice each day in response to the Moon's pull. These body tides are invisible to us because everything around us, buildings, trees, the landscape itself, moves up and down together. Even the atmosphere experiences tides. Atmospheric pressure oscillates in rhythm with the Moon's position, creating pressure waves that circle the globe. These atmospheric tides are much smaller than ocean tides. The pressure variation is only about 0.02% of normal atmospheric pressure, but they're measurable with sensitive instruments, and they affect weather patterns in subtle ways. The Moon also causes tides in Earth's crust that are much larger than you might expect. In some places, the land rises and falls by as much as 20 inches twice each day. This constant flexing generates heat through friction, contributing to geological activity and helping to keep Earth's interior warm and dynamic. But let's step back in time to see how these forces have shaped the Earth we know. In the early days of the Earth-Moon system, when the Moon was much closer than it is today, the tidal effects were extraordinary. Those early tides might have been hundreds of feet high, massive walls of water that would have reshaped coastlines with every cycle. Imagine standing on the shore of the early Earth and watching a tide that rises not just a few feet, but hundreds of feet. The water would surge inland for miles, turning vast areas of land into temporary seas, then retreat just as dramatically. leaving behind enormous tidal pools filled with concentrated organic chemicals. These powerful tides had profound consequences for the early Earth. The constant flexing and stretching of the planet generated enormous amounts of heat through friction, so much heat that it may have kept parts of the Earth's interior molten for much longer than would otherwise have been possible. This extended period of geological activity helped establish the processes of plate tectonics that continue to shape our planet today. Plate tectonics, the movement of large sections of Earth's crust, is crucial for maintaining a habitable planet over billions of years. It recycles carbon between the atmosphere and the interior, regulates global temperature, and creates the diverse geological environments that support different forms of life. Without the early heating provided by strong tidal forces, Earth's interior might have cooled too quickly to sustain the convection currents that drive plate tectonics. More importantly, those early megatides created something that may have been crucial for the emergence of life: vast tidal pools. Imagine the early Earth's coastlines constantly flooded and exposed by these massive tides, creating temporary lakes and ponds where the chemistry of life could experiment with different combinations of molecules. These tidal pools were unique chemical laboratories. As the tide receded, it would leave behind pools of seawater that gradually evaporated, concentrating dissolved minerals and organic compounds. When the tide returned, it would bring fresh supplies of chemicals and wash away waste products, creating a constant cycle of concentration and dilution that many scientists believe was essential for the development of the first living cells. The wet-dry cycles created by tides may have been particularly important for the formation of cell membranes. Simple organic molecules can spontaneously form membrane-like structures when they're concentrated by evaporation, but these structures are usually unstable. The cyclic wetting and drying provided by tides could have helped stabilize these early membranes, allowing them to evolve into the complex cell walls that protect and define all living organisms. Many scientists believe these tidal pools were among the most likely places for life to first emerge. The constant wet-dry cycles would have concentrated organic molecules, allowing them to interact in ways that might have led to the first self-replicating chemicals. The Moon, in other words, may have been instrumental in creating the very conditions that allowed life to begin. The tidal pools would have contained a rich soup of organic compounds delivered by comets and asteroids, dissolved minerals from the early continents, and energy from lightning, ultraviolet radiation, and chemical reactions. The cyclic nature of tides would have provided alternating periods of concentration and mixing, allowing complex chemistry to occur that would be impossible in either static pools or constantly churning oceans. Some researchers have suggested that the rhythm of tides may have been so important for early life that it became encoded in the basic biochemistry of cells. The fact that many cellular processes, from DNA replication to protein synthesis, occur in cycles that last several hours might reflect an ancient adaptation to tidal rhythms. And as life evolved, the Moon continued to play a crucial role. When the first brave organisms ventured from the safety of the oceans onto dry land, one of the most important transitions in the history of life, they likely did so by following the predictable rhythm of the tides. This transition from sea to land, which occurred roughly 400 million years ago, was one of the most difficult evolutionary challenges life has ever faced. Organisms had to develop new ways of breathing, supporting their body weight, protecting themselves from drying out, and reproducing without water. The tidal zone provided the perfect training ground for this transition. Fish stranded in tidal pools would have faced regular periods out of water, creating strong selective pressure for the ability to survive in air. those that could extract oxygen from air using primitive lungs, or that could absorb oxygen through their skin, would have had a survival advantage during low tide periods. Over millions of generations, these adaptations became more sophisticated. Some fish developed stronger fins that could support their weight on land, allowing them to move between tidal pools. Others developed better ways of preventing water loss from their bodies. Eventually, these aquatic pioneers became the first amphibians, creatures equally at home in water and on land. The predictable rhythm of tides was crucial for this transition. Unlike flash floods or temporary lakes that might dry up unpredictably, tides provided a reliable pattern that organisms could adapt to. They knew that water would return twice each day, so they only needed to survive a few hours out of water rather than days or weeks. Even today, the tidal zone remains one of the most diverse and productive ecosystems on Earth. The twice-daily rhythm of wetting and drying creates unique ecological niches that support an incredible variety of life forms, from microscopic algae to large marine mammals. The moon's influence on the evolution of life extends far beyond these early transitions. Consider the fact that many marine organisms still time their reproductive cycles to lunar phases, a behavior that has persisted for hundreds of millions of years. Coral reefs, as we mentioned earlier, release their eggs and sperm in massive synchronized events tied to specific moon phases. This synchronization is so precise that marine biologists can predict coral spawning events years in advance simply by consulting astronomical tables. The corals are essentially using the moon as a cosmic calendar, ensuring that reproduction occurs when conditions are optimal for their offspring's survival. The timing is crucial because coral eggs and sperm are tiny and would quickly be dispersed by ocean currents if released randomly. By synchronizing their reproduction to specific tidal and lunar conditions, corals maximize the chances that eggs and sperm will find each other in the vast ocean. This lunar timing has been so successful that it has evolved independently in coral species around the world. Sea turtles use the moon's light to navigate during their epic journeys across ocean basins. These ancient mariners, whose ancestors swam in seas when dinosaurs walked the land, still rely on the moon's position and brightness to guide them between feeding areas and nesting beaches thousands of miles apart. Many species of fish migrate according to lunar cycles that their ancestors have followed for millions of years. The moon provides a reliable celestial clock that allows these animals to coordinate their movements with seasonal changes in food availability and breeding conditions. Even terrestrial animals show lunar influences that may date back to their marine origins. Some mammals show subtle changes in activity patterns that correlate with lunar phases. Certain bird species time their migrations to lunar cycles, possibly using the moon's light to navigate or taking advantage of tidal patterns in coastal feeding areas. But perhaps the moon's most important gift to Earth, and to the possibility of complex life, is something far subtler than tides, yet far more profound: the stabilization of Earth's axial tilt. Earth's axis of rotation is tilted about 23.5 degrees relative to its orbit around the Sun. This tilt is what gives us our seasons. When your hemisphere is tilted toward the Sun, you experience summer. When it's tilted away, you experience winter. It's a gentle, predictable cycle that has allowed life to adapt to regular patterns of temperature and daylight over billions of years. The seasons create important environmental cues that many organisms use to time crucial life events. Plants use seasonal changes in temperature and daylight to determine when to flower and produce seeds. Animals use these same cues to time breeding, migration, and hibernation. The reliability of seasonal patterns has allowed life to develop complex behaviors and physiological adaptations that depend on predictable environmental cycles. But without the moon's gravitational influence, Earth's axial tilt would not be stable. Computer simulations show that a moonless Earth would experience wild swings in its tilt over periods of thousands to millions of years, sometimes spinning upright like a top, sometimes tumbling nearly on its side like Uranus does today. These changes wouldn't happen quickly by human standards. They'd occur over thousands or millions of years, but they would create climate chaos that would make the evolution of complex life extremely difficult. The computer models show that Earth's tilt could vary anywhere from 0 degrees to 85 degrees without the moon's stabilizing influence. Imagine if Earth's poles suddenly found themselves pointing toward the sun. The polar regions would become blazingly hot, while the former equatorial regions plunged into perpetual winter. Ice ages would come and go, not in predictable cycles, but in chaotic, unpredictable swings that would make it nearly impossible for life to establish stable ecosystems. When Earth's tilt was near 0 degrees, the planet would have minimal seasons. The equatorial regions would remain hot year-round, while the polar regions would be locked in permanent winter. There would be little mixing of air masses between different latitudes, creating a world of extreme climate zones with little weather variability. When the tilt was near 85 degrees, Earth would essentially be spinning on its side. Each hemisphere would experience decades of continuous sunlight, followed by decades of continuous darkness. During the summer decades, one hemisphere would bake under constant sunlight, while the other froze in perpetual winter. Then, as Earth continued its orbit, the seasons would gradually reverse over a period of months or years. These extreme variations would create climate chaos. Ice sheets would advance and retreat unpredictably. Sea levels would rise and fall dramatically, and weather patterns would shift constantly. Life would face a never-ending series of environmental challenges, with little time to adapt to stable conditions. The moon prevents this chaos. Its gravitational influence acts like a gyroscope, keeping Earth's tilt relatively stable. Over long periods, the tilt does vary slightly, between about 22 and 25 degrees over cycles of about 40,000 years. But these variations are gentle and predictable, contributing to the natural climate cycles that life has learned to navigate. These minor variations in Earth's tilt, combined with changes in Earth's orbit around the Sun, create the Ice Age cycles that have characterized Earth's climate for the past few million years. But even these ice ages, dramatic as they seem, are minor compared to the climate chaos that would result from the extreme tilt variations that would occur without the moon. The Ice Age cycles have actually been beneficial for the evolution of complex life, particularly human evolution. The climate changes associated with ice ages created environmental pressures that drove evolutionary adaptations, while the cycles were predictable enough that life could adapt to them over time. This stabilization has allowed Earth to maintain relatively stable climate patterns for billions of years, giving evolution the time and consistency it needed to produce the incredible diversity of life we see around us today. From the vast forests that produce the oxygen we breathe to the complex ecosystems that support everything from tiny insects to massive whales, all of it depends on the climate stability that the moon helps to maintain. But the moon does even more than stabilize our climate. It also acts, in a sense, as Earth's protector, shielding us from some of the cosmic threats that could end life as we know it. The moon's presence affects the orbits of asteroids and comets that venture into the inner solar system. Some of these objects are gravitationally nudged away from Earth by the moon's influence, sent careening off into different orbits that pose no threat to our planet. Others impact the moon instead of Earth, leaving their mark in the form of lunar craters that serve as a permanent record of the bombardment our planet has been spared. Throughout Earth's history, the Moon has likely absorbed countless impacts that might otherwise have struck our planet. Each crater on the Moon's surface represents a potential extinction event that Earth was spared. The Moon, in essence, has been taking hits for us for over 4 billion years, helping to create the relatively stable environment that allowed life to flourish. This protective role is most obvious when we look at the heavily cratered lunar highlands, which preserve a record of the intense bombardment that both Earth and Moon experienced during the first billion years of the solar system's history. Earth would have received similar bombardment, but geological processes have erased most evidence of these ancient impacts from our planet's surface. Some of the lunar craters represent truly massive impacts that would have been catastrophic if they had struck Earth instead. The South Pole Aitken Basin, for example, was created by an impact so large that it excavated material from deep within the Moon's interior. A similar impact on Earth could have sterilized the planet, boiling away the oceans and destroying any life that might have existed. This protective role continues today. While the risk of a major asteroid impact is low in human timescales, over geological time, such impacts are inevitable. The Moon's presence doesn't eliminate this risk, but it does reduce it, giving life on Earth a better chance of surviving and thriving over the eons. Recent studies have suggested that the Moon's gravitational influence may redirect about 20% of potentially hazardous asteroids away from Earth. While this might not sound like a large percentage, over billions of years it represents countless objects that could have caused mass extinction events. The Moon also helps to clear debris from Earth's orbital neighborhood through a process called gravitational sweeping. Objects in similar orbits to Earth can be nudged into different orbits by repeated gravitational encounters with the Moon, gradually removing potential threats from Earth's vicinity. There's another way the Moon protects Earth, one that operates on a much faster timescale. The Moon's gravitational pull helps to stabilize Earth's rotation, preventing it from wobbling too dramatically. This rotational stability is crucial for maintaining consistent day-night cycles and seasonal patterns that life depends upon. Without the Moon's stabilizing influence, Earth's rotation would be subject to chaotic variations caused by gravitational interactions with other planets, particularly Jupiter and Saturn. These variations could cause Earth's day length to change unpredictably, creating irregular patterns of day and night that would disrupt the circadian rhythms that most life forms depend upon. The Moon's influence on Earth's rotation is so strong that it has actually changed the length of our days over geological time. But perhaps most remarkably, the Moon is slowly changing the very length of our days through a process that demonstrates the intimate connection between our two worlds. Remember that tidal bulge we talked about? As Earth rotates beneath it, there's friction between the moving solid Earth and the tidal bulge in both the oceans and the solid rock. This friction acts like a brake, gradually slowing down Earth's rotation. The energy being lost from Earth's rotation doesn't just disappear, it's transferred to the Moon's orbit, pushing it gradually outward and making it orbit more slowly. This is why the Moon is spiralling away from us at the rate of about 1.5 inches per year. It's also why our days are gradually getting longer, about 2.3 milliseconds per century. This might seem insignificant, but over geological time, it adds up to dramatic changes. When life first emerged on Earth, a day was only about 6 hours long. The gradual slowing caused by tidal friction has stretched our days to their current 24-hour length over billions of years. This process is still continuing, and if it continued indefinitely, Earth and Moon would eventually become completely tidally locked to each other, just as the Moon is already locked to Earth. When that happens, though it won't occur for tens of billions of years, a day on Earth will equal a month. Both Earth and Moon will take the same amount of time to complete one rotation relative to each other. Earth will always show the same face to the Moon, and the Moon will hang motionless in Earth's sky, visible from only one hemisphere of our planet. But don't worry about this cosmic fate. It won't happen for tens of billions of years, long after our Sun has evolved into a red giant and fundamentally changed the nature of our solar system. By that time, if humanity still exists, we'll likely have spread to other star systems and may view the Earth-Moon system as just one of many homes we've made among the stars. For now, we can appreciate the Moon's role as Earth's partner in a cosmic dance that has been unfolding for over 4 billion years. This dance has shaped our planet's surface through tides, stabilized our climate through gravitational influence, protected us from cosmic impacts, and even determined the length of our days and the rhythm of our lives. The Moon has been instrumental in creating the conditions that allowed life to emerge from ancient tidal pools, to colonize the land, and eventually to evolve into the rich tapestry of species we see today. In a very real sense, the Moon is not just Earth's satellite, it's Earth's partner in the grand experiment of life. The gravitational forces that bind Earth and Moon together are the same forces that have shaped the evolution of life on our planet. The tides that may have created the first living cells continue to influence marine ecosystems today. The stable seasons that allowed complex life to evolve continue to regulate the rhythms of migration, reproduction, and growth that define the natural world. Even the gradual slowing of Earth's rotation has played a role in shaping life on our planet. The lengthening of days from 6 hours to 24 hours has allowed organisms to develop more complex circadian rhythms, to engage in more sophisticated behaviors, and to build more complex ecosystems. And that experiment, as we're about to see, may be far rarer and more precious than we ever imagined. The conditions that allowed life to flourish on Earth may depend on a cosmic partnership so unlikely, so perfectly tuned, that it might occur only once in billions of worlds. As we drift deeper into our understanding of the Moon's influence, we arrive at perhaps the most profound question of all. Just how special is the Earth-Moon system? In our exploration of countless worlds beyond our solar system, we've discovered that planets are remarkably common. There are likely billions of them in our galaxy alone, with new discoveries announced almost weekly. But as we search for signs of life among these distant worlds, we're beginning to appreciate just how many precise conditions must align for complex life to emerge and thrive. The Moon, it turns out, may be one of the rarest and most crucial of these conditions. Let's start with something that seems almost impossibly unlikely: the Moon's size relative to Earth. Most moons in our solar system are tiny compared to their parent planets. Mars has 2 small captured asteroids, Phobos and Deimos, that are probably fragments from the asteroid belt, irregularly shaped chunks of rock that barely qualify as moons. Jupiter and Saturn have dozens of moons between them, but even their largest, Ganymede, Titan, Europa, Io, are small relative to these gas giants, more like planets orbiting planets than true companions. Earth's moon, however, is about 1/4 the diameter of Earth, so large relative to our planet that some astronomers prefer to think of Earth and Moon not as a planet and satellite, but as a double planet system. The Moon contains about 1.2% of Earth's mass, making it by far the largest moon relative to its parent planet in the solar system. Even Pluto's moon Charon, which is unusually large relative to Pluto, is smaller in comparison than our Moon is to Earth. This size ratio appears to be extraordinarily rare among the thousands of exoplanets we've discovered. Of all the planets we've found orbiting other stars, and we've found over 5,000 confirmed exoplanets, with thousands more candidates awaiting confirmation, we haven't yet found a single example of a terrestrial planet with such a large moon. This doesn't mean they don't exist, but it suggests they're uncommon enough that we haven't detected one among the many worlds we've studied. Our methods for detecting exoplanets are admittedly limited when it comes to finding moons. Most exoplanets are discovered through the transit method, where we observe the slight dimming of a star as a planet passes in front of it. Detecting a moon around such a planet would require observing an even smaller dimming event, which is at the very edge of our current technological capabilities. But even accounting for these observational limitations, the lack of obvious large moon systems suggests they're genuinely rare. Why does the moon's size matter so much? As we've seen, it's precisely because the moon is so large relative to Earth that it can exert the profound influences we've been exploring. A smaller moon wouldn't be able to stabilize Earth's axial tilt as effectively. The gravitational force would be too weak to prevent the chaotic tumbling that we see on Mars, whose tiny moons provide no stabilizing influence. A smaller moon also wouldn't create the powerful tides that may have been crucial for life's emergence. The tidal forces that created those early tidal pools, those laboratory environments where chemistry first began to experiment with self-replication, depend on having a gravitational influence strong enough to move massive amounts of water over continental distances. And a smaller moon wouldn't have the gravitational influence necessary to gradually slow Earth's rotation to create our comfortable 24-hour day. Without this influence, Earth might still be spinning every 6 hours, creating a world of rapid temperature changes and violent weather patterns that would make it difficult for life to establish stable ecosystems. The way our moon formed, through that catastrophic collision with Theia, also appears to be a remarkably unlikely event. Computer simulations of planetary formation suggest that most growing planets experience numerous smaller impacts rather than a single giant impact. For a collision like the one that created our moon to occur, everything had to be perfectly aligned. The impactor had to be just the right size, large enough to create a substantial moon, but not so large as to completely destroy the Earth. Theia was estimated to be about the size of Mars, roughly 10% of Earth's current mass. If it had been much smaller, it wouldn't have created enough debris to form a large moon. If it had been much larger, it might have shattered the Earth entirely. The speed had to be just right, too slow, and Theia would have simply merged with Earth without creating much debris. Too fast, and the collision would have been so violent that both objects would have been completely vaporized, with most of the material escaping to space rather than forming a moon. Most crucially, the angle of impact had to be perfect. Computer simulations show that a head-on collision would have been catastrophic for both objects, while a glancing blow at exactly the right angle could knock off just enough material to form a moon while leaving the Earth intact. The collision that created our moon appears to have occurred at an angle of about 45 degrees, steep enough to transfer enormous amounts of energy and create debris, but not so steep as to completely destroy both worlds. The timing had to be perfect too. This collision happened after Earth had grown large enough to survive the impact, accumulating enough mass to hold together despite the violence of the collision. But it also happened early enough in the solar system's history that there was still a massive object like Theia wandering in an unstable orbit. If the collision had happened much earlier, when Earth was still small and growing, our planet might not have been massive enough to retain the debris that became the moon. If it had happened much later, when the solar system had settled into more stable configurations, there might not have been any large objects left on collision courses with Earth. The window of opportunity for creating a large moon through this mechanism appears to have been relatively brief in cosmic terms. Even more remarkably, the moon formed at just the right distance from Earth. If the collision had created a moon that was too close, it would have been torn apart by Earth gravity through tidal forces, creating a ring system like Saturn's rather than a stable satellite. The Roche limit, the distance within which tidal forces overcome a moon's self-gravity, is about 2.4 Earth radii for a body of the moon's density. The moon formed just outside this limit, allowing it to remain intact. If the debris had formed too far away, the resulting moon wouldn't have had enough gravitational influence to provide the benefits we've discussed. The stabilizing effect on Earth's rotation and axial tilt depends on having a large moon relatively close to the planet. A distant moon, even if it were large, wouldn't be able to provide these stabilizing influences. But perhaps most incredibly, the moon formed with just the right composition and internal structure to remain geologically active for the right amount of time. In the moon's early history, it was much more geologically active than it is today, with widespread volcanic activity that created the dark Maria we can see with the naked eye. This early volcanic activity was crucial for several reasons. It helped to differentiate the moon's interior, separating heavier elements like iron into the core and lighter elements into the mantle and crust. This differentiation process generated heat that kept the moon's interior warm and active for much longer than it would have remained if the moon had been cold and undifferentiated from the start. The volcanic activity also helped to create a more varied lunar surface, with both light highlands and dark Maria, providing different types of terrain. This variation may have been important for the moon's ability to influence Earth's early environment, as the different surface materials would have reflected different amounts of sunlight back to Earth. The timing of the moon's geological activity also appears to have been perfectly synchronized with Earth's early history. The period of major lunar volcanism between about 4 billion and 3 billion years ago corresponds closely to the period when life was first emerging on Earth. Some scientists have suggested that the moon's volcanic activity may have contributed to Earth's early atmosphere and climate, helping to create conditions favourable for life's emergence. The moon's gradual drift away from Earth also appears to be proceeding at just the right rate. If the moon were moving away too quickly, it would have lost its stabilizing influence on Earth's climate before complex life had time to evolve. The gradual decrease in the moon's influence has allowed life to evolve along with changing conditions, adapting to longer days and weaker tides over billions of years. If the moon were moving away too slowly, the tidal forces would still be so strong that they would make Earth's environment too chaotic for stable ecosystems to develop. The incredibly strong tides of the early Earth-Moon system were probably beneficial for the emergence of simple life in tidal pools, but they would have been disastrous for more complex ecosystems. The current rate of the moon's recession, about 1.5 inches per year, appears to be optimal for allowing complex life to evolve and thrive. It's slow enough that ecosystems can adapt to the gradually changing conditions, but fast enough that the moon's disruptive influence on Earth's rotation and tides has decreased to manageable levels. Consider what Earth might be like without the moon, and you begin to appreciate just how many gifts our lunar companion has given us. Without the moon's gravitational influence, Earth's axial tilt would vary chaotically over timescales of thousands to millions of years. Computer models show that the tilt could vary anywhere from 0 to 85 degrees, creating wild swings in climate that would make stable ecosystems nearly impossible. Sometimes Earth would spin nearly upright, like Mercury, creating a world with minimal seasons and extreme temperature differences between the equator and poles. The equatorial regions would be blazingly hot year-round, while the polar regions would be locked in perpetual winter. The lack of seasonal variation would eliminate many of the environmental cues that life uses to time reproduction, migration, and other crucial activities. At other times, Earth would tumble almost on its side, like Uranus, creating periods where the poles alternately experience decades of continuous sunlight and continuous darkness. During these periods, one hemisphere would bake in constant sunlight, while the other froze in perpetual winter. As the planet slowly tumbled, these extreme conditions would gradually shift, but the transitions would be chaotic and unpredictable. These dramatic climate swings would make it extremely difficult for life to establish stable ecosystems, just as species were adapting to one climate regime, developing the physiological and behavioral adaptations necessary to thrive in those conditions. The whole system would shift, forcing life to constantly adapt to new conditions or face extinction. While some simple forms of life might survive such chaos, bacteria and other microorganisms are remarkably adaptable. The evolution of complex multicellular organisms would be far less likely. Complex life requires stable environmental conditions over long periods to develop the intricate biochemical systems and ecological relationships that characterize advanced life forms. Without the Moon, Earth would also rotate much faster. Our days might still be only 6 to 8 hours long, creating a world of constant, rapid weather changes. The Coriolis effect, which influences weather patterns on Earth, would be much stronger, creating more intense and chaotic storm systems. The rapid rotation would also affect atmospheric circulation patterns, potentially creating more extreme wind speeds and more violent weather. The temperature differences between day and night would be less extreme due to the shorter day-night cycle, but the rapid changes would make it difficult for life to establish stable circadian rhythms. Many forms of life on Earth depend on circadian rhythms that match our 24-hour day cycle. These internal biological clocks help organisms coordinate their internal processes with the external environment, timing everything from cell division to hormone production to feeding behavior. On a rapidly rotating world, it would be much more difficult for life to establish these stable internal rhythms. The absence of significant tides would eliminate the tidal pools that may have been crucial for life's early development. These pools, which alternate between wet and dry conditions with the rhythm of the tides, create unique chemical environments where organic molecules can concentrate and interact in ways that might lead to self-replication. Without tides, the boundary between sea and land would be much more static. The constant cycling between wet and dry conditions that tides provide wouldn't exist, eliminating one of the most promising environments for the transition from non-living chemistry to living biology. The reduced mixing of ocean water that would result from the absence of tides would also affect ocean chemistry and circulation patterns. Tides help to mix nutrients from the deep ocean with the sunlit surface waters where photosynthesis occurs, supporting the base of the marine food chain. Without this mixing, ocean ecosystems would be much less productive. Even if life did emerge on a moonless Earth, it would face additional challenges from more frequent asteroid and comet impacts. The Moon acts as a gravitational shield, deflecting some potentially dangerous objects away from Earth and absorbing impacts that might otherwise strike our planet. Throughout Earth's history, the Moon has likely absorbed countless impacts that could have caused mass extinction events on Earth. Each crater on the Moon's surface represents a potential catastrophe that Earth was spared. The lunar highlands, heavily cratered from billions of years of impacts, are a testament to the Moon's role as Earth protector. Without this protection, life would face more frequent extinction events. The delicate process of evolution, which requires long periods of relative stability, punctuated by manageable challenges, would be constantly disrupted by cosmic catastrophes. Major impacts don't just cause immediate destruction at the impact site. They can trigger global climate changes, filling the atmosphere with dust that blocks sunlight and causes widespread cooling. They can cause massive volcanic eruptions on the opposite side of the planet. They can create acid rain that acidifies the oceans and destroys marine ecosystems. The Moon has also played a crucial role in shaping Earth's magnetic field, which protects us from harmful cosmic radiation and solar wind. The Moon's gravitational influence on Earth's molten iron core may help to maintain the convection currents that generate our planet's magnetic field. Earth's magnetic field acts as a shield, deflecting charged particles from the Sun and cosmic rays from deep space. Without this protection, these particles would gradually strip away Earth's atmosphere, as appears to have happened to Mars. The thin Martian atmosphere is partly the result of billions of years of atmospheric loss to space, aided by Mars' weak magnetic field and lack of a large, stabilizing moon. But perhaps the Moon's most underappreciated gift is the gift of time itself, or rather, the gift of stable, predictable time. Before the invention of mechanical clocks, humans relied on natural cycles to measure the passage of time. The daily cycle of sunrise and sunset provided a basic unit of time, but longer periods required other celestial markers. The Moon gave early civilizations a reliable way to measure periods longer than a single day. The lunar month, the time from one new moon to the next, provided a natural calendar unit that allowed humans to plan agricultural activities, navigate by the stars, and develop the complex societies that eventually led to our modern understanding of the cosmos. This lunar calendar system was crucial for the development of agriculture. Knowing when to plant crops, when to expect seasonal changes, and when to prepare for winter required the ability to track longer time periods than individual days. The Moon's predictable cycle provided this capability thousands of years before mechanical timepieces were invented. Navigation also depended heavily on lunar timing. Ancient mariners used the Moon's position and phase to determine their location and plan their voyages. The Moon's predictable movement across the sky, combined with knowledge of its phase cycle, provided a celestial clock that worked anywhere on Earth. Even today, many aspects of human culture and biology retain echoes of lunar timing. The human menstrual cycle averages about the same length as a lunar month, approximately 28 days, though whether this is coincidence or biological heritage remains a subject of scientific debate. Some researchers have suggested that the similarity between human reproductive cycles and lunar months reflects an ancient biological connection to lunar rhythms. Others argue that it's simply a coincidence, noting that many mammals have estrous cycles of similar length, regardless of whether they're exposed to lunar light. Many cultural celebrations and religious observances are still tied to lunar calendars, connecting us to thousands of years of human tradition. Easter, for example, is celebrated on the first Sunday, after the first full moon following the spring equinox. Many Islamic and Jewish holidays are determined by lunar calendars. The Chinese New Year, one of the world's most widely celebrated holidays, is tied to the lunar calendar. These cultural connections to lunar time reflect something deeper than mere tradition. They represent humanity's recognition of our connection to cosmic rhythms, our understanding that human life is part of a larger pattern that extends beyond our individual concerns to encompass the movements of celestial bodies. The Moon has also inspired human creativity and scientific curiosity in ways that have accelerated our understanding of the universe. Ancient astronomers tracking the Moon's phases and movements develop the mathematical tools that would later be used to understand planetary motion and gravity. The Greek astronomer Hipparchus used observations of lunar eclipses to calculate the distance to the Moon with remarkable accuracy over 2,000 years ago. His method, based on careful measurements of the Earth's shadow during eclipses, gave a result within 30% of the true value, an extraordinary achievement for the time. Galileo's first telescopic observations of the Moon revealed a world of mountains, craters and plains that challenge the prevailing view of celestial bodies as perfect, unblemished spheres. These observations helped to establish the principle that celestial objects obey the same physical laws as earthly ones, laying the groundwork for modern physics and astronomy. Newton's law of universal gravitation was inspired partly by his attempts to understand the Moon's orbit around Earth. His realization that the same force that causes an apple to fall to the ground also keeps the Moon in orbit was one of the great unifying insights in the history of science. And of course, the Moon was the first destination for human space exploration beyond Earth. The Apollo program, inspired by the goal of landing humans on the Moon, drove the development of technologies and scientific techniques that revolutionized our understanding of space and our ability to explore it. The technological advances required to reach the Moon, rocket propulsion, life support systems, navigation and communication technologies, materials, science, computer systems, have found applications far beyond space exploration. Many of the technologies we use in everyday life, from microprocessors to advanced materials, have roots in the Apollo program. But perhaps more importantly, the Apollo program fundamentally changed humanity's perspective on our place in the universe. The famous Earthrise photograph, taken by Apollo 8 astronauts as they orbited the Moon, showed our planet as a small blue marble rising over the lunar horizon. This image became one of the most influential photographs ever taken, inspiring the environmental movement and helping humanity see Earth as a single, fragile system. The Moon landing also demonstrated that humans could work together to achieve seemingly impossible goals. The Apollo program required the cooperation of hundreds of thousands of people, the development of entirely new technologies, and the commitment of enormous resources over nearly a decade. It showed that humanity could overcome technical challenges and political obstacles to accomplish something truly extraordinary. When we consider all these factors together, the Moon's unusual size, its unique formation, its perfect distance and composition, its role in stabilizing Earth's climate and protecting it from impacts, its influence on the emergence and evolution of life, and its inspiration for human culture and scientific advancement, we begin to see the Earth-Moon system as something truly extraordinary. Some scientists have proposed what's called the rare moon hypothesis, the idea that large moons like ours are so uncommon and so crucial for the development of complex life that their rarity might help explain why we haven't yet found evidence of intelligent life elsewhere in the universe. This hypothesis suggests that while simple life might be quite common throughout the universe, arising wherever liquid water and basic organic chemistry can occur, the path from simple microbes to complex intelligent life might require a very specific set of cosmic coincidences, of which our Moon is a crucial component. If this hypothesis is correct, then Earth isn't just a rare world capable of supporting life. It's a rare world capable of supporting the kind of stable, long-term conditions that allowed life to evolve from simple chemistry to consciousness itself. The Moon, our silent companion, has been an essential partner in this extraordinary journey. The rare moon hypothesis doesn't mean that intelligent life is impossible without a large moon, but it suggests that such life might be much less common than we might otherwise expect. In a galaxy containing hundreds of billions of stars and potentially trillions of planets, even very rare conditions might still occur millions of times. But the rarity would help explain why we haven't yet detected signals from other civilizations, despite decades of searching. But even as we contemplate the rarity and preciousness of the Earth-Moon system, our relationship with the Moon continues to evolve. After a hiatus of more than 50 years, humans are preparing to return to the lunar surface, this time not just to plant flags and collect rocks, but to establish a permanent presence. The Moon, which gave us the gift of stable conditions for life to flourish on Earth, may now become the stepping stone that allows life to spread beyond Earth to other worlds. Future lunar bases could serve as staging areas for missions to Mars and other destinations, taking advantage of the Moon's low gravity and lack of atmosphere to launch spacecraft more efficiently than from Earth's surface. The resources we've discovered on the Moon, water ice, rare metals, helium-3 that could potentially fuel future fusion reactors, could support not just lunar colonies, but the entire space-based economy that many scientists believe will develop in the coming centuries. In this new chapter of our relationship with the Moon, we're beginning to see our celestial companion not just as Earth's partner, but as humanity's gateway to the cosmos. The same gravitational influence that helped shape the conditions for our evolution may now help us take our next evolutionary step, from a single planet species to one that calls the entire solar system home. And as we prepare for this next phase of our lunar relationship, we might pause to appreciate the profound continuity of our connection to the Moon, the same celestial body that influenced the tidal pools where life first stirred, that stabilized the climate in which our ancestors evolved, that inspired the first humans to look up at the stars and wonder, will now welcome us back as visitors, explorers, and perhaps eventually as residents. But that's a story for the future. Tonight, as you prepare to rest under the Moon's gentle light, you can appreciate the billions of years of cosmic partnership that made this moment possible. The long, slow dance between Earth and Moon that created the stable, beautiful world we call home. And so we come to the end of our gentle journey through the story of the Moon, a story that began with a question about restless nights and led us through billions of years of cosmic partnership, from violent birth to peaceful companionship, from the stirring of life in ancient tidal pools to the dreams of future lunar colonies. Perhaps you've drifted off during our journey together. If so, that's perfectly wonderful. Sleep is, after all, one of the Moon's gifts to us, part of the stable circadian rhythms that our lunar companion helped establish over millions of years of evolution. But if you're still listening, still following this quiet exploration through the night, take a moment to appreciate the remarkable story we've uncovered. Tonight, when you look up at the Moon, whether it's a thin crescent barely visible in the twilight, or a full moon flooding your room with silver light, you're looking at far more than just another celestial object. You're seeing Earth's ancient partner, forged in fire and shaped by time into the perfect companion for our world. That familiar face looking down at you has witnessed the entire story of life on our planet. It has watched over the first tentative stirrings of chemistry in tidal pools 4 billion years ago. It has illuminated the first creatures to venture from sea to land, guided by the rhythm of lunar tides. It has provided the stable seasons and predictable days that allowed forests to grow, ecosystems to flourish, and eventually consciousness itself to emerge. The Moon has been humanity's timekeeper and navigator, inspiration for our earliest art and our boldest scientific theories. It has been the subject of our first tentative explorations beyond Earth, and it may well be the stepping stone to our future among the stars. But most remarkably, the moon has done all of this through the gentlest of influences, not through fire or ice, not through violent intervention, but through the subtle persistence of gravitational embrace. The same force that may whisper to your sleep cycles, that raises the tides twice each day, that keeps our planet's seasons stable and our days a comfortable length. There's something profoundly beautiful about this, isn't there? In a universe often characterized by violence and chaos, stars exploding, galaxies colliding, asteroids careening through space, the moon represents something different, a peaceful presence, a stabilizing influence, a partner rather than a conqueror. The moon asks nothing of us. It makes no demands, sets no requirements. It simply continues its ancient orbit, offering its gifts freely. The tides that may have nurtured life's emergence, the stability that allowed complex ecosystems to develop, the protection that has shielded us from countless cosmic impacts, the gentle light that has guided travelers and inspired dreamers for thousands of generations. And perhaps most wonderfully, the moon connects us to something larger than our daily concerns, larger even than our single planet. When you look up at the moon, you're participating in an act that connects you to every human who has ever lived. The moon that you see tonight is the same moon that guided ancient mariners across unknown seas, the same moon that inspired Galileo to point his telescope skyward, the same moon that drew humanity to take our first steps beyond Earth. It's also the same moon that shines on people all across our world tonight. Someone in Tokyo is seeing the same lunar face you see, perhaps from a high-rise apartment as the city awakens. Someone in London might be glimpsing it through autumn clouds. Someone in the Amazon rainforest is seeing it filtered through the canopy of the world's most diverse ecosystem. An ecosystem that exists in part because of the moon's gift of climate stability. This shared experience of moonlight connects us not just across space but across time. The photons touching your eyes tonight left the moon's surface just over a second ago, reflected from sunlight that travelled 93 million miles from the sun to illuminate the lunar landscape. But that landscape itself tells a story spanning billions of years, every crater a chapter in the solar system's history, every dark plain a memory of ancient volcanic activity. The moon is, in many ways, a messenger from the deep past, carrying information about the early Earth and the violent youth of our solar system, but it's also a beacon pointing toward the future, a destination waiting for humanity's return, a world that may someday host human communities, a base from which we might launch explorations to Mars and beyond. In this long view of time, geological time, cosmic time, our individual lives might seem fleeting and insignificant. But there's another way to think about it. You are made of elements forged in the hearts of stars, organized into patterns complex enough to contemplate the universe that created you. You are the universe becoming aware of itself, if only for a brief moment in cosmic time. And tonight, as you rest under the moon's gentle watch, you are part of an unbroken chain of life that stretches back to those first tidal pools, forward to futures we can barely imagine. The calcium in your bones, the iron in your blood, the water in your cells, all of it shaped by the same cosmic forces that continue to govern the dance between Earth and Moon. The moon's influence on your sleep, whether real or imagined, connects you to rhythms far older and grander than human civilization. If the moon does indeed whisper to your circadian cycles, then in your very dreams you participate in the same gravitational conversation that has been shaping our world for over 4 billion years. But even if the moon's influence on sleep is purely psychological, purely cultural, there's still something beautiful about the connection. The idea that we might still respond to lunar cycles speaks to something deep in our nature, a recognition that we are not separate from the natural world, but part of it, that despite all our technology, all our cities and artificial lights, we remain connected to the ancient rhythms that govern the cosmos. As you drift towards sleep tonight, whether easily or with a gentle restlessness that sometimes comes with bright moonlight, you might carry with you this sense of connection to the moon that has been Earth's partner for nearly the entire history of our planet, connection to all the life that has evolved under lunar light, from the simplest bacteria to the most complex ecosystems, connection to all the humans who have looked up at the moon in wonder and all who will do so in the future. The moon will be there when you wake, continuing its patient orbit, pulling gently at our oceans, holding our planet steady in its course through space. It will be there tomorrow night and the night after, and for billions of nights to come, a constant presence in an ever-changing world, a reminder of the deep time and vast scales that put our daily concerns into their proper cosmic perspective. So rest well under the moon's gentle light. Let yourself be held by the same gravitational embrace that has cradled our world for eons. And perhaps, as you drift off to sleep, take a moment to appreciate the extraordinary cosmic story that made this moment possible. The story of a violent collision that became a peaceful partnership, of a distant companion that helped create the conditions for consciousness itself. Sweet dreams, fellow travellers through space and time. The moon keeps watch over us all, as it has since life began its long journey from the tidal pools to the stars, and in the morning, when the moon fades into the brightness of day, it will still be there, still pulling gently at our world, still keeping us company on our journey through the infinite cosmos. Thank you for joining me on this peaceful exploration of our lunar companion. Until we meet again under starlit skies, may your rest be deep, your dreams be filled with wonder, and your connection to the cosmos bring you peace. Clear skies and gentle moonlight, the sleepy astronomer.